gravitational field as we are continuing the chapter gravitation. So gravitational field, we have discussed a lot about gravitational field, but our discussion was based on the gravitational field due to point masses. And few cases we have discussed like a wire, like a rod, like a seed, etc. Okay, so today's topic is gravitational field, and this time we will try to calculate the gravitational field due to a ring of mass m, radius of the ring, let it be a, O is the center of the ring, and the ring is placed, the plane of the ring is placed in YZ plane, and P is a point lying somewhere on the x-axis. P is a point lying somewhere on the x-axis, like this. Let the distance be x. So we can say what? Point P lies on the axis of the ring, or we can say P is an axial point. P is an axial point. Okay, we will try to calculate or evaluate the gravitational field due to the ring whose mass is m and radius is a. Okay, and it is placed in a plane perpendicular to the line OP, or we can say it what? It is placed in YZ plane. Okay, and P is the point lying on the axis of the ring, so we can say P is an axial point. How to start? We know well this is a continuous mass distribution case where mass is not in a discrete form, mass is not as a point mass is the ring is distributed over the whole length, right? So here radius is a. So what we can say? We can say what? The mass distribution is over the length, so we can say the ring has a linear mass density. The ring has a linear mass density whose lambda is given by m upon mass upon total length of the ring. Total length of the ring is 2 pi a, where a is the radius. Okay. Now if I take a small portion, let us take a very small portion, okay, a length element of the ring. Okay, the length element, let it be dl, and obviously we will define its mass dm, and dm will be lambda dl. It's quite simple to understand this mass element. Now we calculate the field at a point, the gravitational field at the point P due to the point mass that we have considered over here, the element over here. Okay, let us join them two. Join this two. This line, let it be R. Okay, let it be R. This is X, this one is A. R is the distance of the point P where we try to calculate EG at P. Our target is to calculate EG, gravitational field at the point P. Okay, so we have to connect these two, the element and the point, and let the distance between the element and the point, okay, is R. And by Pythagoras we can write down R square equals to A square plus X square, or R is equals to A square plus X square to the power 1 by 2, or square root. Okay, fine. Now the element will have some field over there, and the field, as we know, is what? This field is in the direction radially inwards. So this is the direction of the field DE. Okay, let the distance be R. This is the field DE. What is DE? DE can be written as, we can write down DE as G into dm, mass of the element, G into dm upon G into dm upon R square. Okay, let this line AP makes an angle theta with the x-axis. Okay, we can do what? So this is the direction of the field DE. Okay, let me use another color to show you DA, the direction of DE. DE, since it is always radially inwards, so this arrow shows the direction of DE. I can resolve this DE vector along two axes, one along OP, another perpendicular to OP. Find the component of this along x-axis will be DE cos theta, and the perpendicular component is as usual DE sin theta. As we have seen in the other cases that we have to check the symmetry. Okay, so by symmetry we can take another symmetrical element just diametrically opposite to the initial element. Okay, and again if we join it, if I join this, the angle again becomes theta. This angle, this field is again DE, and this DE will have a component along PO as well as it will have a component on y-axis. That means for all the elements taken, for all the elements we have to take, right? You see, if we take all the elements especially those who are perpendicular to the line OP, they will do what? They will be like this way, that way, that way, that way, right? So these will be like this. There are so many components will be there, and finally, resultantly, what we notice that if there is an element in the vertical upward direction, right? Suppose it is along y-axis, then there is a counter element which is equal in magnitude but opposite in direction to the initial one. That means it should be along negative y-axis. And since these two, see DEY, so these two y components will cancel out each other since they are equal in magnitude and opposite direction. Now say, if because of that, if one of them is like this, so another one will be like this. Okay, so these two, one will be, if one of the element will be along positive axis, then definitely the counter element or the symmetrical element will have a field that have a component towards negative axis. So these two equal and opposite vectors will cancel out each other. So from symmetry test, what can we confirm? We confirm that integration of DE perpendicular component should be 0. So the only parallel one, or we can say the horizontal one, will exist. Fine. So exactly we can write down DE dash. Let it be. Then the elementary field towards along the line PO. Let it be DE dash. DE dash will be DE cos theta. This will be G dm by r square into cos theta. Okay. Now come to the right angle triangle where angle is theta. We can see cos theta is equals to, what is cos theta? Cos theta is equals to base upon hypotenuse, base is x upon hypo is r, or that will be x upon r. Okay, so DE dash, as you have seen, DE dash, okay, this will be G dm by r cube, dm by r cube x. Okay, and obviously it is along the negative x-axis, so we can write down minus of I. Okay, in vector form. So magnitude wise, if you write DE dash only, G will be G dm upon x upon r cube. So G m x upon r cube. What is r cube? R is a square plus x square to the power 1 by 2. So we can write down this as a square plus x square to the power 3 by 2. Okay, and this will be G x upon a square plus x square to the power 3 by 2. This into dm. Right. As you can see in this expression, x is what? The distance of the point P from center of the ring, which is a constant. A, the radius, right? The radius of the ring, that is another constant. So these are constants. Capital G, we all know, universal gravitational constant. So these are all constants, right? Except the mass of the element dm. And so the total field E net, okay? Or if I write E G at P can be obtained. E G at P can be obtained by integrating this term. Or this will be G x upon a square plus x square to the power 3 by 2 integration of dm. Since this ring is made up of uniform elements, right? So the integration of the mass of the element, this will become m. So it will be g and x upon a square plus x square to the power 3 by 2. This is the expression for E, G at P. And this will be minus of I cap. So you can see the case. Here E at P is towards the along the axis and radially inwards, right, toward the center. This is the expression for E at the axial point. E, we can say EG at an axial point. Axial point. The point which lies on the axis of the ring, whose mass is m, radius is a, and it lies at a distance x from the ring. So E, this can be given as Gm, where m, capital M, represents mass of the ring, Gm x upon a square. Eg at the center of the ring. Eg at the center of the ring. What does it mean? If you want to get Eg at O at the center, that means E gravitational at O will be obtained by putting x equals to 0. So putting x equal to 0 here, x into whatever is 0, 0 upon whatever is 0. So this will be Eg at O is 0. That means there is no gravitational field at center of the ring. But at the same time, if I put x equals to infinity, see Eg again tends to infinity when x tends to infinity. Okay, at a distance x infinity plus whatever will be infinity, anything upon infinity will be 0. That means the field reduces to 0 at infinity. That means the field extends up to infinity. So it is 0 at 2 points, one here at the origin, other somewhere at infinity. Now, if they ask you to find the point or the distance of the point from center of the ring where the ring has a maximum value of gravitational field. Okay, that means if they want to get the point, the distance x, find x for Eg maximum. Find x for, they ask you to find x for Eg maximum. Since E at G is given as, in this expression, number 1, gmx upon a square plus x square to the power 3 by 2. So what to do? We know well from maximum minimum concept, okay, if for any value of x, if E is maximum, then dEg upon dx will be 0. And by making it 0, first derivative of the function must be 0. That is the rule of maximum or minimum, right? So whether it is maximum or minimum, first derivative must be 0. dE upon dx will be 0. And by solving this, we get x. And I'm not going in the detail of solution. You can do it. You know the formula. Explain. Okay, differentiation. You have learned it. Okay, in fractional form, what to differentiate it. Okay, then finally by making it 0, we get x is equals to a upon root 2. X is equals to a upon root 2. Where a stands for radius of the ring. That means at any point here, suppose Q, right, which is at a distance x is equals to a upon root 2, the field will be maximum. So field is maximum there, and we can, how can we show this in graph? In graphically we can show it like this. At origin we have seen the first case, Eg at the center of the ring is 0, Eg at O is 0. That means here it is 0. At here x equals to a by root 2, it's maximum. It's maximum somewhere. And what the maximum value? The value of E max will be, the maximum value of the gravitational field will be obtained by putting x equals to a by root 2. So we can put it Gm. X means a by root 2 upon R cube. That is a square plus x square square. X square means a square by 2 to the power 3 by 2. Okay, we can solve it later on. This is the maximum value of the gravitational field at a point where at a point which is a distance x is equals to a by root 2 from center of the ring, and we can show it over here. This is the value of E max. Okay, and graph goes like this. After that, it drops, and finally it tends to right. It shows a tendency of touching the x-axis. Right, it goes up like this, and then it drops like this, and finally it shows a tendency of touching. So it will be Eg will be 0 for x equals to infinity. So it will show a tendency of touching the x-axis, but not here. It will show at infinity. That is the graph. Take care. In some cases, they may ask you the graph problem, but the graphs are asked with a little bit change, where they don't put the values only. The graph plotted is given like this. The graph to be plotted it may be given like this. Let it be Eg and let it be x. Okay, in that case, obviously, where since Eg is towards negative ix, negative I cap, or that is towards negative x axis here in this case, so this graph must be plotted like this. Okay, where it should be negative and this is the minus of this. That is what the case of calculating E for a ring. There are so many other cases we can find out for a ring, for annular ring. Okay, and the most common examples of the things or the objects due to which we calculate the gravitational field is a sphere. A sphere, right? Obviously, a sphere, and second one is a spherical cell. Spherical cell. What is a spherical cell? What is the difference between a sphere and a spherical cell? I hope you all know this. Sphere and a spherical cell. Sphere is solid throughout, whereas spherical cell is hollow from inside, or we can say a hollow sphere may be called spherical cell. Okay, and we can calculate it easily. So let us see. We have a spherical cell, okay, whose mass be m and radius is r. Okay. Due to after taking elements etc., I am not going in that detail right now, but just for convenience I am telling you the results, final results. Okay, due to the how does E varies with r or x. Okay, and let us see a point P. Let us see a point P here somewhere inside the sphere. Okay, and the point P is at a distance r from here. Here you can see point P. Case 1, point P lies inside the cell. Point P lies inside the cell. Point P lies inside the cell, or that can be written like this: small r is less than capital R. The distance of the point from center of the sphere, center of the cell, is less than its radius. So small r less than r. And just note down the final results and okay, learn it, keep it in your memory. Okay, it will be a shortcut one. You will be able to apply directly in the questions, the numericals. So P lies inside the cell. If P lies inside the cell, that is inside a spherical cell, small r is less than capital R, and E, G at P will be 0. That means there will be no gravitational field anywhere inside the cell, whatever be the point. If it is inside, okay, don't worry. And if the point P, suppose, lies outside, if that is the distance is smaller, okay, if that lies outside, that means the point Q. For the point Q lies, what you see? Q lies outside the cell. Q lies outside the cell. You can frame the conditions like this, where small r, for that means Q is an external point that is lying outside the sphere, and for which small r is greater than capital R. Then EG at Q is given by G capital M by small r square. And obviously, since all fields are radially inwards, which is the direction. Okay, G. And third case, if the point lies on the surface of the cell, then if the point lies on the surface of the cell, say a point S lies here like this. So a point S lies on the surface. So for point S, what we can say? For point S, small r is equals to capital R. Just replace the small r. What I get? EG at S is equals to EG at S is given by GM by capital R square. What you can check just by comparison. Comparing these all three cases, what you notice? Let us conclude that gravitational field inside the hollow sphere, wherever it may be, the field value will be 0, whereas if it is lying outside, it will be Gm upon small r square. But if the point lies on the surface, it is Gm by capital R square. By comparing all these three cases, what we can see? This one is the maximum. This one is the maximum. And if they ask us to plot a graph, let us learn this graph also. E versus R graph. E versus R graph. Since this is radially inverse, opposite to the vector R, it means in vector form I can write down this as EG at Q can be written as minus of Gm by R square R cap. Unit R cap is unit radial vector. We are almost familiar with these things, right? So, how to plot the graph? It is 0 inside. That means from R equals to 0 to R equals to capital R. To R equals to capital R, there lies no field, and the moment we reach the surface of the cell, what you notice? We see a maximum field over there, and this maximum field, since the quantity over here, right? E, the field, EG and R, both are given vector terms, so we have to take care of the sign also. So that should be plotted in the graph, must be plotted in the fourth quadrant. Okay, and here we can see like this. This point is what? Minus of Gm by R square. What? After that it obeys inverse square law, or we can say EG varies inversely with R square, hence the graph will be a parabolic curve which tends to touch the R axis at infinity. So this is what? EG proportional to 1 by R square. This is the graph. Before that there is no graph. Okay, there is no field inside. It is clear for all. We can do it like that. And similarly, let us see some other cases. That means if I put a point mass anywhere inside the spherical cell, it will not experience any kind of pull. Okay. Let us say the case of a solid sphere. In case of a solid sphere or sphere, right? In case of a sphere, the case is very simple. Okay, and once again I am telling you the results. Let us say we have a solid sphere. Okay, as usual, I will take this is a solid sphere whose mass is m, radius is capital R, as usual, right? And let me consider 3 points. One lies inside. Let the point is P. And it is small r. Case 1. In the first case. Again come back for P. For the point P. What is the condition? Small r is less than capital R. And then, yeah, here is the thing changing. Here E, G at P is given by G M by R cube into small r. Gm by r cube into small r. That is the expression for E at internal point. And here what you see, things to be written, seen over here, Eg is easy at an internal point. At internal point. Easy at an internal point of a sphere, varies directly with its distance from the center. It varies directly with r. Okay. Similarly, second case, if I consider at any point Q, and where is the Q? Let us take Q somewhere outside. Let this be point Q, and the distance is now r. Okay. This Q lies outside. Q at Q, that is an external point. At an external point. Okay. At an external point it is there, and then at an external point it should be written as r greater than capital R, and since it is an external point, there is no change. Eg will be equals to Gm by small r square. Yes. But please remember, all points will be relatively inverse. So in vector form to write, you have to use the minus r capital there. And third case, when at say a point S which is lying somewhere on the surface of the sphere. At S, for S, or you can say for the point S, condition is small r is equals to capital R, or you can write down Eg at S will be Gm by capital R square. This is what the situation with the three cases, right? Three cases are as usual. First case, when the point lies inside the sphere, that means small r is less than capital R, and the field comes to be Gm small r by r cube, where it shows that Eg at an internal point of a sphere is proportional to r, directly proportional to r. That means E varies linearly with small r. The distance means as we go toward the surface, right, we can see the field is increasing. And obviously from there, one thing from this discussion, if small r is 0, that is what? That means E at O will also be 0. Why? Small r is 0 at O, and since small r is 0, putting 0 over here, 0 into whatever is 0, so there is no field at the center of our sphere. Okay, so these results are there. Now come back to the graphical explanation. We have a graph. We want to put a graph over there, E versus R for a sphere. E for RE and R for the sphere. See, it starts at origin, at the center of the sphere. It is what? 0. That means for R0, it will be 0. But second thing, beyond R, right? When R is not 0, but R is greater than 0, but less than capital R. Small r is greater than 0, and here the first second case, right? It shows what? That the field varies linearly with small r, and we can say there is a straight line. This was what? Eg varying linearly with r. Up to what distance it varies linearly? Until you reach at the surface of the sphere. When you reach the surface of the sphere means the third case for S, small r equals to capital R, Eg is equals to Eg at S will be Gm by r square. You can check, since capital R is less than small r for external cases, right? Then we can say what? This is the maximum value. Okay, so you feel which is the maximum value, but yeah, don't do the mistake. Here the things are in vector, so plot it in the fourth quadrant, and you will have a maximum value of the gravitational field when you reach where? At the surface. That means at small r is equals to capital R. The value is minus of Gm by r square. Okay, and beyond that means we are talking about all the points who are lying outside the for a point r greater than capital R, small r greater than capital R. Okay, we have to see the follow the case 2 where Eg is varying. Here you can see Eg is varying. inversely with square of r. So definitely, and we know well the graph going to be a parabolic curve. Okay, which tends to touch the r-axis, but not here. It will touch at the infinity. This is what the graphical study on how the gravitational field due to a sphere varies with distance from the center. Okay. Now, in doing that, why did we learn this part? We learn this part as we are more able to know the gravitational field of Earth, our own planet, right? So, gravitational field. Now, we'll try to learn the gravitational field of our own planet, the Earth. Okay. We are interested right now, we are trying to learn the gravitational field of the Earth. Yes, we talk about, this time we will talk about our own planet Earth. And what does the Earth look like? Earth looks like a sphere, right? Which is a sphere. In fact, it is not a perfect sphere, right? A bit flattened from at the poles. Okay, that means its radius is not uniform. Okay, it is not a perfect sphere, but just for the calculation, just for the sake of studies, we are taking it. Simply, we are just considering it as a perfect sphere. Practically, it is not a perfect sphere. Its radius and a line, you know well, divides the Earth into equal halves. This line we call equator, and here are the two poles. Okay, and this is the center of the Earth. This distance is known as equatorial radius, equatorial. And this distance, this length we call polar radius. In Earth actually our polar is less than our equatorial. Okay. Mean radius is 6400 kilometers, no doubt about that. But let us see, for the sake of studies, we can consider it as it has a lots of impacts, right? So many effects are there. Our life is dependent, we are alive because of this gravity, and there are so many other things, okay, which can't be imagined even in absence of gravity. Whatever beauty, whatever things you see all around you, it is there because, and they are there for so many years, it is because of the gravity of the Earth. Okay, so this is a very interesting topic. Let us see, this is our planet, okay, the Earth, and that is the point O. We know well our Earth, let M represents mass of Earth. Let M represent mass of the Earth, and R represents radius of the Earth. R represents radius of the Earth. Okay. M represents mass of the Earth, R represents radius of the Earth. So we can repeat the process. We have just learned how to find out gravitational field due to a solid sphere, due to a sphere. Our Earth is also a sphere, right? It may not be a homogeneous one who's having a uniform density throughout. It may not be a perfect sphere, right? But this time we are not considering these things. We are just trying to derive an expression which will give us the gravitational field of the Earth. Very simple to understand. Say it is a sphere. We treat our Earth like a solid sphere, and solid sphere or sphere of mass m and radius r. And here are the points. Let us take the points. Okay, when we have just learned that the gravitational field due to a sphere is maximum at its surface. Okay, let us see a point P over here. Let us see the point P. At P, so EG due to the Earth at its surface. At its surface, that is R is equals to capital R case, right? So, and this is what we know well, EG due to the Earth at its surface is always maximum. Don't forget what we have just learned for a sphere. Okay, and its maximum and its value is Gm by R square. Gm by R square. Okay. Similarly, and point outside. somewhere else, right? You know the things, gm by small r square, inside gm small r like r cube, the things are there, gm by r square. Now see the other thing. Let us have a body. Let us put a body here at the surface, at the point P, which lies on the surface of the earth. Okay, and if small n represents mass of a particle, right? Mass of body. Small n is the mass of a body placed at the center, at surface of the earth. At surface of the earth. Definitely. Yes, we also know that whatever is on the surface or outside the surface, beyond the surface or inside the earth's surface, right? Whatever there is a force of attraction. Earth pulls everything towards itself. And we also know that pull of the earth is known as the pull of gravity. So, when the body of mass small m is placed at the surface, there must be a force of gravity acting on it, and the force of gravity acting on it acts towards the center. And that force of gravity, what we call weight of the body. This force of gravity, the force by which earth attracts anything towards its center, is known as force of gravity. This is not gravitational, right? But the term gravity, a specific term. The term gravity, force of gravity or simply gravity. So gravity is exactly what? Gravity is nothing but a term specially associated with our planet Earth. So gravity is nothing but a nickname you can say, is a gravitational pull of Earth. Gravity is the term that is used to represent the, to make it special, right? Because it is our own planet, we have to take care of it, we have to study it. Now life depends on it. Well-being. So we have assigned a different name, a specific name, gravity. The word gravity directly means what? Gravity exactly means gravitational pull of the planet Earth. Okay, this term gravity is not used for other planets present in the universe. Okay, or the planetary system, solar system. It is a term specially assigned or okay to the planet Earth. Okay, so gravity of Earth is what? What is the gravity? Of the gravity acting on the body? How much gravity is acting? Or the force of gravity acting on the body? Okay, force of gravity acting on the body is force of gravity acting on the body is known as weight of the body. Weight of the body. Okay, and what is the weight of the body? Its mass. We know well, its mass into G. What is G called? Where G is known as, this G is called, since G is force by mass, right? So dimensionally, you can check it is having a dimension of acceleration, and force upon mass is called acceleration. But this acceleration, since this is the force, this gravity is the experienced gravity, force of gravity experienced by the body of mass small m kept at the surface of the earth is what equals to mass of the body into G, the acceleration due to gravity, okay, where G is equals to F by m. So it is what? Nothing but acceleration. And the term this is acceleration. This acceleration is provided to the body of mass small m by our planet Earth, and this acceleration due to force of gravity. So this G, that's why the term G is called acceleration due to gravity. Okay, check over here. Acceleration due to gravity. This is what? Force by mass. Okay, fine. Here the field is, come back to the next topic here again. Eg due to the earth at its surface is gm by r square. If gravitational field at P is gm by capital R square, then the gravitational force experienced by the body, of mass small m will be small m into Eg, and that will be gm small m by r square. Okay, this is the gravitational force experienced by the body, and here we also see this is nothing. This gravitational force and the force of gravity of the body both are similar things, right? So what we can write down? G m upon r square is equals to small m into g, the weight of the body. Okay, since these two m's we get cancelled, and you can see g, the term g is equals to gm by r square, and this g, since we are calculating this at the surface of the earth, we all know well that this is the maximum value of g, hence we preferably to identify that it is the maximum value of g, that is at the surface of the earth, g is written with g naught. So g naught is gm by r square. In our other calculations right now, okay, we will put g naught wherever g naught comes. Okay, be aware that it is the value of acceleration due to gravity at the surface of the earth. So g naught is gm by r square. Now, since g, or the field, right, is not uniform everywhere, but it is uniform only on the surface of the earth. At anywhere, if I take this body, it will have the same weight, or you can say it will experience the same acceleration due to gravity. But yes, if the distance of the body from center of the earth is changed, definitely the acceleration due to gravity experienced by the body will be different. And since this is different, the weight of the body will be different. Mass, you see, since g varies. When we talk about the term W, weight, W is mass into G, this M. Okay, in Newtonian mechanics, okay, when the bodies are at rest or not moving so fast, we consider what? Mass to be constant. So, okay, mass is a constant. Which one is variable? G is variable. So, what makes the weight variable? The variation in G, acceleration due to gravity. So the variation in weight, that means at different places, that is at the surface of the earth, the body will have different weight. Okay, at certain height you go, okay, at the altitudes, right? Yes, the weight will be different, and okay, a body will have no weight, weightless. When the body is at an infinite distance from the earth. The concept of weightlessness is something else. Okay, I will tell you later. Please don't mix up this thing with the G0 at infinity. Here we can say G tends to 0 when R tends to infinity. This is not the case of weightlessness in the satellites. Okay, in the space ships, yeah, this is not the condition, or never explain the weightlessness condition in space ships from this concept. Because there R is not infinite. So small m is constant, is fixed. So G varies, okay, and we have seen also, again we have seen the graph how G varies. So this time we learn the variation in G, the factors responsible for variation in G. Since G, as you see, as you have seen, the G, acceleration due to gravity, and acceleration due to gravity by the planet Earth is given by G m by r square, or we call it G naught, G at the surface, right? At any distance r, okay, at any distance r from the Earth's surface, yes, it will be Gm by small r square. When small r is the distance of the body from center of the earth. Okay, and capital R explains the radius. So small g naught is Gm by r square. Okay, see, we will now discuss the factors on which, due to which G is observed different at different places, even on the earth surface or in the specific altitudes with depth. Okay, not only that, even at different places of the earth, we also observe different values of G. We know it is 9.8, okay, but it is not same everywhere. This is the average value we have taken. Okay, so this time we will learn the factors on which G varies from place to place. Variation of G. This is now our topic of discussion on what factors does G vary. Okay, we have first seen that our Earth is not a perfect sphere, or the first factor is non-sphericity of the Earth. Yes, non-sphericity of the Earth. Even measure, let us see the case. We have the Earth. This is the axis of the Earth, geographical axis. Okay, this axis is there, and the line, there is an imaginary line which divides the Earth in two equal halves. Okay, two equal halves. This line is known as equatorial line, or is called equator. Equator. This is called equator. So equator does what? Or equatorial line does what? Equator divides the Earth in two equal halves. Okay, the upper pole is known as North Pole. The lower pole is known as South Pole. Hence, the equator divides the Earth in two equal halves. Okay, northern hemisphere and southern hemisphere. Okay. Now this is the center of the Earth. Okay, this radius is called equatorial or equatorial. Okay, and that one O to P, this radius is known as polar radius. Since Earth is a bit flattened at the poles, one can understand that you have learned in lower studies also. It looks like an orange. Okay, poles are a bit below, right? Bit depressed. Okay, so we can say what? R poles is less than R E. Okay, R P is less than RE. Since G or even G naught, since G naught varies inversely with square of the distance. We have seen G naught is Gm by R square, even at the surface of the Earth. See how these interesting things are there. Okay, G at the surface of the Earth varies. G at the surface, that G naught varies inversely with square of the R, and since RP is less than RE, polar radius is less than equatorial radius, and therefore G at the poles is going to be greater than G at the equator. Okay, that means if I take 2 points, one, or if I take the weight of a body at 2 points, one that is at the poles, that is point A, and say B. Okay, it will experience less weight at the equator and more weight at the poles, since the polar radius is less, where radius is small. Okay, the value of G is more, and therefore G at the poles is greater than G at the equator. That means if you have a body, okay, whose mass is M at the equator, its mass at the poles will be bit more than that. So this is one factor on which the variation of G takes place, or we experience different weights even on different places of the Earth. Okay, let us now talk about the second factor. Second factor of the Earth. Okay, and second factor is what? Yes. Non-homogeneity of the Earth. Non-homogeneity of the Earth. Okay, or this is what? Not a homogeneous sphere. Homogeneous means what? Let us see. Since this is Earth, okay, let its radius be R, mass be M. Then it is, since it is a sphere, its volume is 4 by 3 pi r cube. Okay, since it is a sphere, its volume is 4 by 3 pi r cube. This is the volume of the Earth cube. Okay, since this is the case, rho, or from there we can find out the value of R. So, okay, so rho is the density. Since Earth is the middle of the Earth's surface or body of our Earth is made up of different types of rocks. If you go inside, there are gases, there is molten material, there are solid rocks. Okay, there are solid rocks, tectonic rocks, you know it. Okay, mines, coal, so many things are there. That means you can't say that in any, if I take a volume, equal volumes from different regions, right? You will not be sure that both these volumetric elements will have the same mass. Why? Because of the fact density is not uniform. Earth is not an homogeneous sphere. Since Earth is not an homogeneous sphere, right? Its density is not there, and in place of this, we can put over there, right? And in place of this, you check mass. If I put mass, then m will be, m can be written as 4 pi r cube into rho upon 3. Okay, 4 pi r cube into rho upon 3. This is the mass, and we know well g naught at the surface is g m by r square. So g by r square into 4 by 3, 4 pi r cube into rho upon 3, r square to r cancel, or we can say g naught is directly proportional to rho, where r is kept constant. So this is the scenario. Okay, g naught is directly proportional to rho, where density is more, value of g will be more. Okay, if I replace m by this rho, a rho comes over there. That means, yes, there is one more factor. Why? Even at the same depth from the surface. Let us take these 2 points we have just mentioned. Okay, and these 2 points over here are A and B. Since these 2 points are, suppose they are at the same depth h from the sun. Okay, but you will not find the weight W at A will not be equals to W at B. Why? The weight of the body is not equal to at A and B. Not equal at both the points. Why? Because the density of the Earth is not uniform everywhere. So this factor, which it becomes a reason, okay, which appears to be a reason of variation in G, is non-homogeneity of the Earth. There are some other factors also and some questions also. Very interesting part, and this part, okay, attracts so many questions. The examiners, the paper setters, they usually play hot cake for paper makers, paper setters. So they ask almost every year. They prepare this topic to ask questions. Okay, we will discuss it. The discussion will continue.